Hi everyone, Felix. Today I'm going to talk about our work, MAGMA, an optimization framework for mapping multiple DNN on multiple accelerator cores. In today's talk, I will start with a background introduction of multi-sub-accelerator architecture, then set up the background of scheduling problem inside this architecture, and then describe the design space of it. Then I will share our proposed solution, which covers a scheduling optimization framework M3E and a search algorithm MAGMA. Then I will show some evaluation results and conclude this talk. Now let's take a look at what a canonical DNN accelerator is made of. First, we will have PE array. In each PE, there could be 1 to several ALU or MAC unit. Second, we'll have hierarchical buffer. For example, small local scratchpad beside each PE, share global buffer, and off-chip DRAM. Third, we need network-on-chip NOC to distribute and reduce the data. These three basic components are the most high-order bit of hardware resources we need to configure in the DNN accelerator and then formulate the hardware design space. Also, we have mapping, which tells how the DNN workload are mapped onto the accelerator. It includes several components. For example, each decision of tiling, compute ordering, Parisian dimension, and mapping shape will together affect the efficiency of the DNN accelerator. These four formulated the mapping space of a DNN accelerator. Now we have described the architecture of a single chiplet DNN accelerator. Let's look at what multiple chiplet DNN accelerator looks like. For higher performance or multi-tenancy use case, researchers start to package multiple accelerators together and connect it with interconnect. Essentially, each accelerator chiplet becomes a sub-accelerator in the package. We call it multi-sub-accelerator architecture. For example, Google has chip package with multiple dice architecture. NVIDIA has Simba, which is multi-chip modules. AMD use multiple PE array in their architecture, and Hero use multi-heterogeneous data flow sub-accelerator architecture. Spanning from single accelerator to multiple sub-accelerator, it creates a new design space across sub-accelerator. To optimize the decision in this design space is a target of this work. First, let me quickly go over a single accelerator. In single accelerator, we have hardware resources and mapping space, where hardware resources include PE, buffer, and NOCs. In mapping space, we have tiling, ordering, Parisian, and shape. Now we consider multi-tenancy workload and multi-sub-accelerator architecture. Now we have multiple jobs to schedule to different sub-accelerators, and how we schedule will hugely affect the overall performance. And this scheduling, we call it global mapping. And the mapping in the sub-accelerator, we call it local mapping. In this work, we assume the heterogeneous multi-core accelerator are given. That is to say, the sub-accelerator hardware resources and the local mapping part are fixed, and we optimize the scheduling or global mapping of it. Next, I will share how we describe the design space of this. First, let me set out some context on our system assumption for our multi-sub-accelerator architecture. The accelerator will receive the workload from host via HBM. In the accelerator, there are several homogeneous or heterogeneous accelerators. Each sub-accelerator will fetch the workload from the HBM via the shared system bus bandwidth, which bus bandwidth is limited. To optimize the performance of the accelerator, we will run a schedule optimization process and send a scheduling strategy to the controller in the accelerator. The goal of this work is, given a set of workload, a multi-sub-accelerator architecture, and optimize the schedule. Here, let me describe the target use case of this work. First, multi-tenancy DNN workload in cloud or edge data center. Essentially, multiple purpose DNN run simultaneously. Some applications like photo auto editing, image tagging, video processing, voice processing, and so on, will bulk of the job need to be run with different models, and we want high throughput of them. Second, we will run this application in a group or batch inference manner, and jobs in each group have no dependency with each other. The independency of each job can come from because they are different DNN model or from the same DNN model but different mini batches. Finally, the schedule is optimized offline. Since application often being run again and again, so we will search the optimized schedule first for the series of applications that we have in the platform. Now let's see how the schedule works. Here we have 6 jobs and n homogeneous sub-accelerator. The first thing we want to do is sub-accelerator selection. Essentially, pick a sub-accelerator to run the job. There could be multiple potential strategies, for example, random or round robin. Or we might come up with a heuristic like idle accelerator first, essentially assigning job to whichever accelerator is available. Let's say we use idle accelerator first. Then now we have our initial schedule. So what to consider next? The shared bus bandwidth. Because concurrent jobs are going to share the potential and potentially contain the limited bandwidth, we might want to reorder the job for bandwidth load balancing. Then it makes the second part of the scheduling job ordering. Now let's see a slightly more complicated example. Here we have heterogeneous sub-accelerator. It means each sub-accelerator could have different strengths, some good at convolution, some good at jam, and so on. Therefore, each job has different execution time in different sub-accelerators. One useful heuristic sub-accelerator selection might be minimum execution time, meaning we always critically pick the sub-accelerator that can run the job the fastest. However, as you may already notice, it could also incur unbalanced allocation like this. Therefore, we will also need to reorder the job for sub-accelerator load balancing. After that, don't forget we still need to do bandwidth load balancing again, and potentially iterative this process again and again. So the complexity of this iterative optimization is tremendously high when considering heterogeneity, sub-accelerator load balancing, bandwidth load balancing together. And the complexity will exponentially increase with the number of jobs. As we've seen previously, the design space of a schedule includes 2 parts, sub-accelerator selection and job ordering. For M sub-accelerator architecture running n jobs, the sub-accelerator selection could have big O m to the n choices. And jobs ordering complexity is like this. So n divided by m means the average number of jobs in each sub-accelerator, and they can have different permutation. And we'll do this for all the n sub-accelerator. Here is a simple example with 2 accelerator and 5 jobs. There are 2 to the 5 choice of sub-accelerator selection, and 2 factorial and 3 factorial choice for job ordering, which gives 384 choices. Here we give a more realistic example with 4 sub-accelerator and 40 jobs. It has more than 10 to the 50 choices. If we exhaustively search through it, the search time will be longer than the age of Earth. So before we go into our solution, let's see an example of how the schedule affects the performance. We use this schedule for 2 sub-accelerator and 5 job cases. And this is their runtime performance. The color means the time each job takes on its assigned accelerator. Let's assume we have another schedule, schedule B. Its runtime performance is as shown, which takes longer time to finish than schedule A, and becomes a less ideal schedule. So what could be the potential issue? First, inefficient peak of sub-accelerator. For example, green job might be run faster as sub-accelerator 1, but it is allocated to sub-accelerator 0. Second, bad bandwidth load balancing. For example, both green and yellow are bandwidth intensive jobs, and we schedule them to run concurrently. Third, bad sub-accelerator selection, sub-accelerator load balancing. For example, sub-accelerator 1 is already idle after yellow job is completed. However, red job is allocated to the sub-accelerator 0. Here's our solution. First, we'll talk about our framework, M3E, a multi-accelerator mapping explorer. M3E takes in the input of workload, which is multiple DNN, the system configuration, including the configuration of each sub-accelerator, system bandwidth, and so on, and an objective. In our case, we always use maximum throughput as our objective. Then it will go through M3E optimization framework and generate a schedule. We'll describe each block in the following slides. First, Workload Analyzer. It introduces a hardware cost model, Maestro. Maestro is a detailed analytical cost model that can model arbitrary local mapping and local hardware implementation. We use it to model the performance of sub-accelerator. The workload analyzer will take in the input of workload, which is a group of jobs with no dependency, and the system configuration, including each uniquely configured sub-accelerator. Then it will generate a job analysis table. It captures the performance of each job running on each accelerator. It records no slow latency. Essentially, it is the best possible execution time, assuming no resource contention. And bandwidth requirement. Essentially, it is the required bandwidth to achieve ideal no slow latency. Or you could think of it as maximum bandwidth consumption of this job. This job analysis table is generated at initialization stage and will be reused throughout the optimization process. Next, bandwidth allocator. It allocates the shared system bandwidth across sub-accelerator. It will take in the candidate schedule generated by the optimization algorithm and also fetch the job analysis table information. So if you want to know more detail about how bandwidth allocator use the job analysis table information, please look at our main paper. So here's an example. It will look at the concurrent job from the schedule and allocate the bandwidth by our algorithm, and the system bus bandwidth could be usage is shown as follows. Then the M3E simulator will run the two jobs until either of them finish. At this point, the bandwidth allocator will fetch the next job, assigning it to sub-accelerator 1, which is idle now, and allocate the bandwidth and run it until one of them finish, and the process goes on. Finally, bandwidth allocator will generate a runtime profiling of each sub-accelerator, which goes into the fitness evaluation. Here are the other components of M3E. First, decoder. It will decode the parameter into schedule. Then fitness evaluation. It will score the schedule based on objective. Then optimization algorithm. It could be any of the shelf or customized search algorithm, such as black box like genetic algorithm, the differential evolution, particle swarm optimization, and so on, or IO-based manner. It could also be customized scheduling algorithm like AMT or HARO. In this work, we use MAGMA. And finally, initialization. We use random initialization as default, but we also have a technique called warm start, which will let algorithm converge faster. And if you want to know more detail, please look at our paper. Here we introduce how M3E represents a schedule. First, we have jobs, and then they could be put into schedule like this. Then in M3E, we'll represent the schedule with a series of parameters like this. The parameter space is essentially where each optimization algorithm is working on. And we use integer value to indicate the accelerator selection and the floating point value to represent the order. For example, this parameter can be decoded like this, which match the schedule we want to represent. Next, we look at our optimization algorithm, MAGMA. MAGMA is a GA-based algorithm, so let me use 30 seconds to refresh our memory of genetic algorithm. In genetic algorithm, we have evolution part and evaluation part. Evaluation part is essentially our cost model. Evolution part is the search algorithm. At the start, you will initialize a population. There are multiple individuals in a population. Each individual has multiple genes. Then we use some operator like crossover and mutation to perturb their genes, evaluate them with cost model, and select the good one as the parent of the next generation. And then start all over again, iterate until the algorithm converge or reaching the runtime or sampling limit. The efficiency of the algorithm actually comes from the customized operator. For example, this is the mutation operator. And these are the corresponding change at the schedule after mutation. We have 3 customized crossover as follows. First, crossover gene will cross over a region of either of the section, and crossover range will cross over a region of both the sections simultaneously. And crossover sub-accelerator will inherit the entire schedule of a certain sub-accelerator. And all these operators are designed to preserve different portions of the information while keep exploring. And if you want to learn more detail about this and what's the implication of them, please look at our paper. So we can often judge a search algorithm by sampling efficiency. Essentially, it is about how fast it converges and how good it converges to. Here we show the convergence curve of 2 cases, where y-axis is the throughput and x-axis is the number of samples. We can see that mutation only performs badly, and when we incrementally add a design operator, it converges faster and better. Each operator increases the sampling efficiency of the algorithm. Next, let's see some evaluation. Here is our evaluation methodology. Workload, we look at vision, language, and recommendation workload and the mix of the 3. System, we consider both homogeneous and heterogeneous sub-accelerator architecture. We configure multiple architecture settings as shown in the table. Sub-accelerators are heterogeneous in terms of different P array sizes, different local mapping, and different buffer sizes. We compare with several baseline algorithms, AMT-like and Hero-like, several black box, and 2 RL-based manner. Here we compare algorithms in different cases. First, vision and mix here means workload. Small and large accelerator corresponding to the accelerator configuration we show in the last page. And we compare the achieved throughput of different algorithms. So here, the higher the better. Many algorithms work well in single domain workload on small accelerator cases. And reinforcement learning and MAGMA consistently work well across all cases. And MAGMA is in average 1.3 times better than 2 IO manner. Here we show the convergence curve of 2 workloads. We can see MAGMA converge faster and converge to better point because of its higher sampling efficiency from the domain-specific operator. To try to understand how different algorithms explore the design space, we visualize them on a 2D dimension plot by PCA projection. Each dot means one design point in the design space. The darker the color means higher performance. In this plot, we use exhaustive search and let it run for days to best effort capture the space. Then we want to see how each algorithm search this design space. Here we show the sampled point of different algorithms. Also, the final throughput performance of best found solution of each algorithm. We can see that different algorithms converge to different regions, and MAGMA samples a wide region at the start and converge to a higher performance region quickly. Here we show a sample of found schedule of MAGMA and comparing with one of the baseline from Hero-like schedule. Here we can see MAGMA reach better performance. Maybe it's because it's picking more efficient sub-accelerator for different jobs. So it might be a little bit difficult to tell what is actually the reason why MAGMA is performing better from this plot. However, if we plotted out the bandwidth usage across its runtime, then we can find MAGMA does a much better job on bandwidth load balancing, which becomes one of the key reasons it reached better performance. Conclusion. Multi-tenancy on heterogeneous DNN accelerator becomes increasingly popular recently, and many multi-tenant applications comprising groups of certain production DNN model are run continuously and in large scale in edge or cloud data center. So there are huge performance optimization rule space by rescheduling their execution order and accelerator allocation. And MAGMA proposed a customized GA scheduling algorithm targeting this use case. We propose a scalable scheduling representation and 4 customized exploration operator for sampling efficiency. And MAGMA consistently show better performance than other comparing methods. If you are interested in our work, please look at our main paper. Thank you.